Hi, everybody. Thanks so much for joining us today for our Seal Connect Classroom webinar, Simple Pump Field Tests with Chris Tyndall. Chris, thanks so much for joining us today.
Thanks for having me.
Of course, of course. While we're letting folks come in and join the webinar presentation, I wanted to ask you a question. Since you're talking about, kind of what you can do in the field, what are some reasons why some folks just do not trust their gut when they're in the field if they think something's wrong?
That's a good question. I guess trusting your gut, there's probably, for me, it's analysis paralysis. There's just so much information coming in today that, we can get caught up in the weeds of just trying to sort through data. And even though we have a feel or an idea of what's going on, just because we're in the local environment, I think we can try to justify our decisions through just too much data, and trying to simplify that is part of getting back to that gut of knowing what to do and how to address a problem.
Awesome. Well, thanks for answering that question. I think we are ready to get started. Again, this is Simple Pump Field Test with Chris Tyndall, and it is part of the Seal Connect Classroom webinar series that we have been doing since March of 2020. You can join the chat on social media using the hashtag SealConnect. There is a question section on the right-hand sidebar of GoToWebinar. So if you have any questions at all, go ahead and start asking those. And if it's something super timely, I will jump in and interrupt Chris and ask the question. If we can wait until the end, I'll do that as well. So don't hesitate to ask questions of Chris while we're going through the webinar. There is a handout section. About midway through this presentation, Chris will talk about an Excel spreadsheet that he developed around temperature and vibration that can help you guys. And we encourage you to download that so that you have it available to you. And we also will be recording the webinar. It's currently being recorded. We will send you the recording and a PDF of the slide deck sometime tomorrow. And remember to ask questions. We're going to also be asking some polls, and don't forget that handout. And Chris, I'm going to turn it over to you. Please take it away.
All right. Thanks, Lori. Thank you guys for joining us today. My name is Chris Tyndall. I am a regional business manager for SEPCO, covering the South Central Gulf Coast, Texas area. And I've been in reliability for a little more than 20 years. Spent most of my career in the inspection services side of the business. And so using predictive technologies, instrumentation, sensors, and such to gather information about assets, machinery, and determine the health of and how that impacts systems. So spent a majority of that time in consulting and working in PSM, developing programs and RCM programs using sensor information. So thanks for joining us. The agenda today is, I'm not sure if I have control. There we go. The agenda, what we really want to talk about is basic knowledge, simple tests that we can use to evaluate the health and condition of machinery assets. We'll talk about instruments, the overall type handheld instruments that can provide temperature, vibration, instruments for our testing methods for oil analysis, and also just talk about our basic 5 senses, how to use our senses, our visual, hearing, smell, and feel to really assess condition of equipment in the field. So before we begin, we have a poll. And Lori, would you launch the poll for us?
I will do that right now. You guys should see it. Do you use IoT enabled technology or sensors in your plants? We just want to kind of get an idea of how many of you are using sensors and how many aren't. So please answer, and someone answer, because I'm not going to close it until we get some responses. Um, so if you are not using them, that's fine. We're going to be able to help you with some of the techniques that you can use to use when you don't have sensors. All right, we have a good number who have answered. So let me close it. Oh, we had some more answers. I'm gonna wait one more minute or one more second, not a minute. Okay, we'll close the poll and let's share the results. So 20% say yes and 80% say no. So I think this is going to be very beneficial to everyone who's on the webinar.
Awesome. All right, that's really not surprising. What may surprise you is the amount of sensor technology that's actually in the market. So there's what we see a lot of is that there's sensors out in the field that are not being used, and we'll talk some more about why we believe that is and how that may, how we may be able to improve that. But there's sensors on everything, whether it be flow and level, speed, pressure indications. There are sensors that measure vibration and sound, stress, strain. There's positioning sensors. There's literally sensors on everything that you can imagine. And some of that information is being streamed into our operating systems. We're able to bring that into a DCS and trend values, make decisions with that information. So, but there's a lot of sensors out there that are even visual sensors in the on equipment, and they may light up, indicating the health of an asset being red or green. It's what I see a lot of, especially with vibration sensors and such, that people tend to turn those off because at night it looks like a Christmas tree, and then the phones ring because something is red and someone has a question. So I can see why sensors, there's such a large gap from actually using sensors. But on the other hand, that's a good reason to remind ourselves of the basic tests that we can do to evaluate the health of an asset in the field. When we talk about refreshing basic knowledge, engineers coming out of college, they understand sensors. They understand the technologies, how they're applied in equipment design. And so we have sensors coming out on valves, on pumps, on motors that are able to communicate Bluetooth, wireless to gateways and communicate values that could be useful to us. What is missing is that a motor is a motor, no matter, when it comes out of the factory, they're all the same. The pumps are all the same. For the most part, they valves and such. It's all about the context of how it is installed and applied in the field that really defines several of the condition assessments that need to be done. One of the things that, let me see, I'm still not seeing, Lori. I'm still not being able to move. Okay, there we go. So advanced sensors, with sensor technology, the ability to measure an equipment vibration or temperature has become more readily available, and sensors are very focused on a single point. And so bringing that information in to a larger analysis using a tool to to be able to organize that information, because a sensor is only as smart as what we tell it. And so the sensor is giving us a value that can be useful, but in the context of all of the other information, that's where you can end up with information overload. You can bring in too much information, and all of a sudden you find yourself showing up for work and everything is in alarm. And so if everything is in alarm and everything is requiring attention, it overloads the system and ultimately can hide real problems in the weeds of all of the false positives. And so using the sensors and using our own senses, looking at a system, is where true value can be found. Um, so refreshing us on how to use our basic senses, how to step back and look at a system, look at the operating context of our machinery, and decide uh, what is actually going on using, our human senses of touch and feel and sight, sound. Those are critical to really assessing a larger system. Looking at, let's consider a pump, for instance, in its operating context. Now, there's tools that are available to us. There's overall temperature. I think in today's environment, everyone is keenly aware of handheld temperature instruments, the pyrometers that are able to give us temperature that we're using through anything from COVID testing to machinery testing. It's those are low-cost instruments that are that can provide us with a go no go condition of temperature. And one of the things to consider when you're evaluating a system is that overall temperature uh, can really it's not a value that you need to trend on non-critical assets. There's certainly temperatures that are critical that we may want to trend in a DCS to be able to see any kind of changes or trigger alerts for critical assets. But just for the balance of the plant uh, machinery, being able to set a temperature that's a go no go. So one that comes to mind is that we've used in the past for general balance of the plant motors and pumps, is to take an infrared gun and to scan an asset from the driver to the driven component, and to look for any anomalies, anything that say is over 150 degrees Fahrenheit. That's a simple scan that can be done in a matter of seconds per asset. And when you let go of the trigger of most of these instruments, most of these handheld guns, it's going to tell you what the max temperature was. So there's the visual aspect that an operator or a maintenance technician who's doing the evaluation, there's a visual that they can see as the temperature changes across the opposite drive in to the drive in of the machine. You can see, let's say the temperature swings from 120 to 138, and but if you have an anomaly in there that's something over 150, then you can stop and you can isolate that, and it may be, let's say for instance the inboard motor bearing is running at 158. Uh, those are the things that you set a go no go that just says, hey, on your PM sheet, only document the ones that are abnormal. If everything was below 150, you would just check the box saying that everything was good. There's no real need to maybe trend that information, and then have like an upper limit that says at 170, 180, you actually want to generate an immediate work request to for someone to do a detailed analysis, or to send out your PDM inspection group to look at this asset. So that's a good way to use overall temperature. This is a simple bubble chart that's used to collect anything from sound to vibration to temperature. Just doing a hand sketch or downloading something like this into a PM sheet enables you to lay out a thermal profile and to look at a machine to determine where the hot spots are, where is the temperature radiating from. You may have an anomaly that's showing up on one side of the machine that's being caused by or the source is on the other. And so when you map this out on paper, uh, it gives you that visual system approach, a system view or a bird's eye view. Um, so overall temperature, thermal profiles can help us compare like machines. And really, one of the things that I always stressed is that I grew up on Sesame Street, and so I always like to look at what is not the same here, what looks different, comparing other machines that are alike in kind, looking at what is changing, the round peg in the square hole kind of thing. Just simple stuff that we learned in prior to grade school. I mean, the stuff that we literally learned on Sesame Street is exactly what we need to simplify what we're looking at, what is actually going on, and stepping back and using just our basic senses. Taking an overall temperature is another way to do that would be using your hand just to feel around, and you can literally feel a machine and determine where a source of heat is coming from. But an overall temperature helps you to quantify that in a way that's useful, and it's actually repeatable. So overall temperatures, there's tons of tools that we can use, anything from our hand to digital thermometers, thermocouples, pyrometers, and all the way to infrared cameras. And honestly, the technology has gotten to the point to where you can buy some of the lower end thermal cameras with simple uh, detectors that are still a 120 by 80 or something that's a low resolution, but it still gives you that visual, just like if you were creating the thermal bubble plot map. The infrared camera is able to actually color that for you and create a visual for the eye to see where temperature is radiating from. And I always start with temperature because that is the most basic element of reliability. That is something that when things that are rotating and moving start to go bad, it starts in the ultrasonic realm where parts are starting to rub together, where I have a stationary and a rotating component that are now touching. Two things are going to happen. First, I'm going to get friction, which is going to create some ultrasonic sounds that can be detected using ultrasonic instruments. They may not early on. They're not so much detectable by our human ear. That's limited to the frequency range below 20,000 hertz. But with an ultrasonic instrument, we can amplify those sounds. Now, what happens next? Friction leads to heat, which can be detected with these instruments. And so using thermal instruments is a very low cost, inexpensive way to get early detection of the health and of our equipment. So the next one is vibration. So what happens next if two components are starting to contact and we have that ultrasonic element that's starting to generate frequencies that can be detected and even trended? There's ultrasonic instruments that we didn't include in this presentation, but it's a precursor of vibration. So in a way, when you think about something that's rubbing, I have a stationary and I have something that's moving back and forth, that is creating sound that can be, there's low cost instruments that we can use to contact and detect an overall value that is an amplitude value that can be set just like the temperature that we talked about. You can have a go no go that is you're using to look at decibels and say within this decibel range, if it exceeds 130 or 140, whatever the decibel is that you're trying to trend, you can have a trigger point that is based off of using the Sesame Street values. What is the average for that machinery type? But temperature will start to increase as components start to rub together. Well, eventually, what will happen is you will lose clearances inside of machines. So bearings, uh, different gears, could be impellers, whatever is rubbing that it was not designed to rub. These components, stationary and rotating components, are supposed to be separated. And if something happens and they start to contact, it will over time transition from ultrasonic through temperature to finding its own clearance again. When that happens, then you're starting to move into the lower frequency realm where our vibration sensors start to pick up the problem. And so bearings, any kind of rubs and such like that it can be detected using vibration. It could be a looseness condition. One of the good things about vibration is that low frequency stuff, like say for instance a loose bolt or a loose foundation, if something's rotating and we have a fastener that becomes loose, the machine will start moving in that direction. So the forces are starting to move in that orientation, which would be in line with the fastener. So as long as we remember what we're looking at when we take the vibration reading and we're taking on the top of the machine, you're relative to the fasteners that are trying to hold the machine down. And so whatever that orientation is, whether it's a vertical machine, it could be left and right, or it could be up and down, but you're looking for the source of, and using the same bubble plots and such, you can start to diagram the actual machine. So horizontal, vertical, axial positions. That's something that no matter what sensor we're dealing with, whether it's a vibration sensor, temperature has more of a uh, non-directional. It can expand out more so than some of the others, but it still is going to point to a source. The same thing with ultrasonic. If I have something I'm measuring sound and I'm trying to determine the point of origin, it's highly directional. So the higher the frequency, the more directionally focused it is. So trying to determine whether it's coming from the vertical direction up and down, the horizontal directions on the machines relative to the bolting, the foundation, and then the axial positions in line with the shafts. Those are all giving us information about what's going on with the machine, and being able to diagram that is something that is useful. So the next slide is actually referring to the handout that we have. One of the things about vibration analysis. So when we take out a simple overall vibration tool, uh, and we start to measure the machine, it's if everything was cleared out and you just wrote down the values on the bubble diagram, you're talking about changes in vibration that could be anything, let's say in the velocity side, because most of these instruments will give you a velocity reading in inches per second, and then it will also give you an acceleration value in G's. And the difference between those two, you'll see in the top of this chart, just a basic idea of what the information is pointing to. The lower frequency stuff that shows up in the velocity spectrum could be related to imbalance, misalignment, looseness, later stage bearing issues, could be uh, anything from belts and such. But rotating looseness, stationary foundational looseness, while on the other side, the G's reading that shows up in acceleration is looking more at impacting, rubbing, flow related turbulence and such like that. So if I just had a blank canvas and I started writing in values, it's hard for us to visualize what we're looking at, especially to the untrained eye or somebody who's not looking at these values constantly. So all the spreadsheet is basically enabling you to give yourself almost like a infrared camera view. It gives you a thermal or a visual of where the anomalies are, where are the higher values. So in the spreadsheet, what you'll find is that in these blocks, you can enter in the values in the horizontal, vertical, and axial directions, and you can start to highlight, or it will highlight the colors based off of in the top left-hand corners of each one of these trend or one of these plots. There is an alert value and an alarm value. So if in this case it's 0.3 inches per second, 0.4 inches per second would be an alarm, and so anything below 0.3 it colors it green. And you can adjust that up and down based on the machine that you're trying to evaluate. So if you want to look at anomalies that are below 0.2 inches per second or 0.15 and maybe alarm at 0.3, you can do so, and it will start to shade the blocks in accordance with that temperature profile. So it gives you a transition from green to yellow to orange and red. And so in this case, you can see just by plugging in the information, and down at the bottom, it gives you a plot of each one of the readings. So as you plug in those values, it'll also plot it and give you high and low level alarms to give you a visual of the machine and its profile to see where the higher values are. So in this case, it appears that in the velocity spectrum, you have 0.36 inches per second in the axial direction at the coupling side, but it does not translate over to the motor. So that would visually give you an indication that you're likely not looking at a coupling issue or an alignment issue. The majority of the energy is in the acceleration side, and you can see that it is isolated more on the coupling side bearing. And in this case, this is a fan, and you can see that the pedestal bearing, it could be a fan or a pump or whatever, but you can see that that it kind of points your eye towards where the issue is. And so gives you a system view of what's going on. And then from there, you can sketch out piping, you can sketch out foundational stuff. Another thing you'll find above the blocks that's not really shown here is that there's a drop down above each one of the blocks that allows you to put in phase angle information. So it just gives you a directional arrow that allows you to put in phase information to show how machinery is moving together or apart from one another as the sensors are measuring, because that's other information that could tell you that you have a loose foundation or you have a alignment issue or such. So simple tool. It can be used for vibration. It can be used for ultrasound. It could be used for temperature. So those are that's in the handout section, and I just found that to be useful. So it's something we created just to help us evaluate condition. You could simply take a picture of the machine, and so overall vibration. Of course, I think where humans have the advantage, sensors are only as smart as what we tell them, and it's giving us information that's very directional. So, for instance, with the vibration sensors, if I measure vibration in a vertical axis, I'm only receiving what that sensor is seeing in that axis. So the machine may actually be, or it's likely moving in a circular pattern, but the sensor's only seeing what I tell it, or what it can within its limited scope. And also sensors could be limited to something that's say for instance the limits of the sensor could be overloaded, may not be sampling at the right frequency, could be something where the machine is actually limited in its ability to move, and so a sensor is showing you a rub or something in that regards. Those are all useful points of information, but stepping back and looking at the machine, this is something that is a challenge for us to always keep in mind. Uh, in today's operating world, there's we have the ability to stream information into our offices. And so we're able to see in the control rooms trending values for vibration and temperature and flow and pressure, and forget that really walking out to the machine can give us the answer to what is going on. So if something goes into alarm, being able to step out and just evaluate the machine, use your hands or using the overall meters for vibration and temperature to probe the machine can give you a quick visual of what the problem is. It could be a loose bolt. It could be anything in that regards. But piping, it could be the vibration is coming from an external source. And so being able to look at multiple machines, one that comes to mind that just came to mind, I remember a machine that there was a resonant condition to where when this pump operated at a certain frequency, the whole stairwell to this tank farm would vibrate and sing like I mean, it was like playing a guitar. But when it ran at a certain frequency or a certain speed, that's what triggered the external vibration. So vibrations can be coming from other sources as well. So being able to walk out, use our other human senses, we get a better systems view of what's going on. So that's vibration, and the next one is oil. Uh, the oil and lubricants, they're the lifeblood of the machine, and so there's a ton of valuable information that can come from looking at oil samples, and there is a lot of information that comes from oil samples. So that data has to be filtered and to make it useful. And so anomalies can happen, and really pulling together information from the field can help us determine whether that they're valid, it's valid data or not. And so we'll dive deeper into that. The oil sampling at the machine, when we take a fluid sample, an oil sample, there's pressure gauges, there's color changing desiccant breathers, there's sight glasses, there's other visual indicators surrounding the machinery and the lubricant that give us clues as to what is actually going on with the lubricant. Um, Oil sampling is great, but differential pressure gauges is something that we need to remember. I think this is one of the areas that is I find is least used. There's pressure gauges all over machinery, and yet we have not identified where the operating context of those gauges. You'll find a lot of times the gauges are fouled or not working, and those are useful tools to determine whether a lubricant system is maybe you have a filter that's bypassing. So it's one thing to take an oil sample and send it to a lab, and then to come back and find that the oil was dirty, only to go back out in the field and find out that the filtration system is being bypassed because the filters were plugged, and so using differential pressure gauges, looking at flow restrictions, or maybe there's a pump going bad, could be a number of things causing the issue. But uh, one of the things that you may find with oil sampling is that we send off samples that are visually bad, and so we take a sample of oil, and you can see that it's oxidized, or that it's contaminated with water or particles floating around in the lubricant, and we still send those off to the lab versus stopping where we're at, using that visual information looking at the system, and then correcting the problem. So we want to uh, we want to continually remind ourselves that, there's more advanced techniques that can be used in the field that do not cost us 40, $50 by the time that we even more than that. I mean, a sample can be as much as $100 by the time we pull a sample. The handling of those samples, coming and going, the analysis of the data. We're spending a lot of money on oil samples that sometimes a quick visual sample at the machine can give us everything that we needed to solve our problem. Color changing desiccant breathers. This is another area that I think is often neglected. And if you walk out into your plants, I want you guys to, take this challenge. Go out in the plant and look at pressure gauges, look at desiccant breathers, and just do a quick survey of one unit, one area, and find out how many gauges are there. Maybe do a count, and there's 50 gauges or 20 gauges, and maybe 20 or 30 desiccant breathers, and then document the current condition of those breathers, of those pressure gauges, of those filter systems, and I think you'd be surprised. It's often neglected. It's one of the most useful tools that we have, and honestly, the lubricant is the lifeblood of our machine. So we want to take care of that lubricant, which translates to improved reliability across the board. Protecting the lubricant is essential. The other thing would be sight glasses, level controls, looking for foam, aeration, water contaminants. Sight glasses is another one of those to add to your list. What is the condition of your sight glasses? Again, take a small sample, decide, and determine what is the health. And those are some of the simple things. That's the low hanging fruit that can be implemented today that can impact reliability immediately, and give you valuable information about what's going on. Uh, Simple field tests before we send off an oil sample to do a 25 element analysis of what's in the oil, whether it's silica or iron or copper. How many particles are in the oil, and what is the viscosity, what is um, the water contamination. Those are all things that can be done on a large scale in the office. So you're able to take a sample and look at separation of water. Just take some time. If it's a machine that is not clear and bright, take a quick oil sample, let it settle out. Use a magnet. Using You can create filter patches. The technology for using magnification and being able to bring that up to a screen. I mean, for under $100, you can buy a microscope nowadays that can feed right into your computer. You can quantify sizes, shapes. You can start looking at what actual particles sub 40 micron are in your oil. And really, when you hold up an oil sample and you look at it, the human eye can typically only see above 40 microns, which is about the size of a dot. If you took a pen and tried to make the smallest dot that you can make on a white piece of paper, clean piece of paper, that is roughly a good example of what we can visually see. So the particles that are below that, the 10 micron particles, the 6 micron particles, 3 micron particles, we can't see those without magnification. And the technology exists to be able to pull a sample. You can use a magnet to stir in and pull any kind of ferrous materials out of a sample. There's just so many things that we can do in our office if something's not clear and bright, to really make decisions immediately that are useful. So oil sampling data, there's just a ton of things that you can do there. There's viscometers. that you can use on site and so forth. So I know I worked in the oil lab side of things for a couple of years, and I was just amazed at how many samples come in that are just grossly contaminated, and someone's asking what's going on. And sometimes this is after a machine's failed. I can see doing wear debris analysis on that to try to get ideas. But a lot of times it's just monthly reoccurring samples that really we should have done something with immediately when we pulled the sample. Or you find out that someone took the sample from the bottom of a sump and it's not a true representative sample of the machine. So again, going out to the machine, looking at the system, deciding whether the information is valid or not, is where we really can come in and improve our analysis using simple tests. So uh, outside of more of the instrument side of things, just using our ears, this is something that we really should focus on. And when we're training new operations, maintenance, engineering, we really need to remember the simple techniques that using your ears, using listening for abnormal noises, getting again towards that. This really dips into the Sesame Street stuff, because what does not sound the same today that from yesterday. Those are things, listening for modulating sounds coming from your equipment, whether it's the wah 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 kind of stuff, or it could be a gravelly noise coming from cavitation, could be recirculation in a machine, could be rubbing. I mean, as things start to rub, they move from the ultrasonic realm down into an audible side. And then there's the old school, putting a screwdriver to your ear and listening to the machine, using a stethoscope to listen to the machine. Those are things that are very useful, that we still need to focus on, because if we don't talk about this, people don't do it. We just lose it. We assume some things that are happening or that are getting passed down through tribal knowledge, and really PMs, we do need to talk about these. We need to go out and practice some of this stuff, and I believe that's an essential part of our training, our onboarding and continuing training for personnel. um, so beyond your ears, there's other aspects of using, um, listening for sounds, cavitation, worn belts, friction, rattling of check valves. Those are things that can be taught. I mean, those are sounds that people need to be familiar with and know how to respond to. Sometimes we hear these things, but we're not. There needs to be a trigger to say whether it's good or bad, a go or no go, and then there needs to be a defined action. So if I hear cavitation, what should I do? If I hear worn belts, how should I respond? That should turn into a work request. It needs to get into our systems, and then evaluate whether it's a condition that's acceptable or not. So uh, using your ears is a big part of it, but probably one of the best and most underutilized is our eyes. And so visual inspections, that to me is a cornerstone of equipment uh, condition monitoring. Uh, Most everything has a visual clue. If you have sensors, it's still important to walk out. I talked about this briefly. If information is coming into the control room that says that I have an anomaly in vibration or temperature, I need to go out and visually look at what's going on. Uh, Look at the entire system. Uh, Look at the driver, the driven, the transmission sources. Things like worn belts. I mean, you can hear that, you can see that. Using strobe lights is another low cost, effective way to tune in to the rotating speeds of various components. It could be a drive shift, or could be a shaft turning. Being able to tune that in to the actual rotating speed, then you can see clearly whether you have, say, a belt issue, something moving, something that's misaligned or worn, you can start seeing evidence of that. The low level stuff that should be part of our 1 minute inspections. When we walk out and we look at the oil levels or process fluids, looking for leaks, looking for cracks, breaks in assets, vibrating piping, noting the base plate conditions. Those are all things that are visual that need to be included in our PM processes. Something that what I like to do is to list some of the most common things that you could see, and then have someone walk through and only notate the ones that are abnormal. So, for instance, at having a checklist that's the procedure has someone walk through some of these things, looking for leaks, spits, sputters, any kind of lubrication related issues. Is there a sight glass issue? Is the breather? What's the condition of the pressure gauge? I like including that on a PM sheet that may have just a list of all the assets with a list of some of the most common uh, issues that you're looking for. So you develop a 30-second, 60-second assessment of the machine when you're walking by, and all you're doing is, once you've trained someone to look for all of these things, it just gives them a place to document that either none of these existed or one of these existed. Another thing that you can do is you can add this to a PM that basically says, is it something that you were able to fix in the moment? If not, then there should be a follow-up work request that says that I was doing a PM of this particular asset, and uh, there was an issue with the oil level. The sight gauge was not visual. It's corroded or stained and needs to be replaced. I mean, those should turn into work orders in the system so that we maintain our processes. So very essential. It's if all we do is spot problems and we never fix them, one of two things is going on. Actually, one of three things is going to happen. Either A, we had a predefined inspection and people just gave up on it because they felt like there was no value. B, we may find that there is no value. We may look and say that, well, that's being over PM'd. The go no go side of things needs to be adjusted. Maybe we are going to live with that for some particular asset. In those cases, we simply just note that in our PM, saying this particular asset is known for these issues, and until we can resolve it, it's just understood. But that's the clean way to get value out of your system, because people will either not follow the procedure because they don't believe in it, or B, they're going to adjust the procedure to something they do believe in, or C, you just didn't have a procedure, so people just make it up as they go. And you're going to find in your processes one of those three in your PM process. So using your nose is another thing that's underutilized. Of course, if something's smoking or is burning, people tend to respond to that. But there's other smells that can be used even when you take an oil sample. You can look visually for oxidation. You can smell oxidation. You can smell whether maybe a lubricant has been contaminated with another foreign substance. It may be a different lubricant. It may be that you smell sulfur smell because someone poured a gear oil in a pump, or vice versa. You may have just the smell of oxidation or mixing of diesel or whatever process fluid in the lubricant. So, but smelling of burning belts, smell is something that is very useful and should not be neglected. I think that's something that we should talk about. Simple tests that should be passed on purposefully versus just passed on through tribal knowledge of how a system should look, smell, sound like, and being able to detect those are things that I think we have an advantage on the human side of things. Now, being able to quantify those, I think the other tools, vibration, temperature, ultrasound, oil analysis, very useful in really quantifying. But even subjectively, there's some objective measures that can be defined, but subjective stuff is just as valuable. So using your nose is another valuable asset. And I think that brings us to the end. Key takeaways, using data and supplementing that with field tests and using our own senses is critical. So I hope that we were able to show that, remind everyone that that observing oil levels, filters, simple gauges, using our simple tools, the inexpensive stuff, putting together toolkits for vibration, temperature, using stethoscopes and stuff like that, ultrasonic meters. Those are low cost things that we can implement into our processes that add tremendous value. And it really comes down to experience, guys. It's if we practice these things, if we are intentional about teaching and training people to observe the simple test, I think it helps us to define a system approach. And ultimately, I think that's the key. I mean, from what I found so far in my career, the system is really important. And when we get narrowly focused into a single data point or a single value, and we forget to step back, look at the system, that's where I think we can make mistakes. And a pencil, a piece of paper, those are all extremely valuable, and I'm hoping useful. I'm hoping you guys can find some use with the Excel sheet. Maybe take that to another level. You can modify that and use that as needed, but I found that to be useful and in the past. So glad to share that. And with that, again, thank you for your participation. We want to open up for conversation, questions, anything that you might want to ask. So thanks, Lori.
Yeah, of course. Thank you so much for that great presentation. Someone had a comment before I start asking a question. I used vibration detection devices in the past with good results. Temp detection is good. However, I had inaccurate readings when operating in a hot environment in the Caribbean. Overall, what you're sharing is valuable. All these assessments are clearly based on field experience, which is great. And I am going to ask the first question, and y'all, we have time, so please drop questions in the question section if you'd like. The first question is, sorry, I'm looking away, I'm looking at my notes. So if you could only track one thing, you've talked about oil analysis and vibration and temperature and ultrasound. If you could track one thing, what do you think would be the most useful thing to track?
I always start with temperature, just because it's the most common. It's the easiest to use. One of the things I think the comment is spot on. Especially in hot environments. One of the limitations, and understanding the limitations of the instrument, when you're let's say you're using an infrared pyrometer, and you're in a hot environment where there's radiant heat, something that's reflecting, or there's surrounding environmental heat. Uh, those instruments could be prone to error, just because you're getting an average of whatever the surrounding environment is. And so spot size, I've seen one of the common mistakes I've seen is that people stand too far away. In some cases, they're trying to zero in on a spot, but by the time you are several feet away, 3, 4, 6, 8, 10 feet, the spot size starts to increase. And so you're looking beyond just that single point, and you're taking in the average temperature of what the environment is. Or it could be a reflective environment where you may need to get a flat paint or something like that that's not reflective. But there's other temperature probe methods. There's contacting temperatures. When you get into the hot environments, that's something that I would consider. It's just maybe looking at a thermocouple or something that's a contacting probe to be able to get an accurate measurement of that spot. So, but temperature is my favorite. It's the easiest to roll out with, probably followed by ultrasonic. So.
Okay, great. We had another question that came in. First, the comment, well done, which I concur. They asked, and this is specific because I think you've worked with this person in the past. Can you tell me the next pump teardown class that you have had in the past? We have sent people before, and they want to send someone again, and they said you can respond by email, but if you know when you might be doing a class again, that would be great. Otherwise, I will make sure to pass the email on to you so that you can answer.
Oh, certainly. Yeah, no, I think there's been a lot of talk about that, doing some additional classes and trying to share information around pump rebuilds, pump reliability. So more to come on that. Definitely, we'll reach out to them. If you'll share the email, we'll try to coordinate something so we can always pull something together on a personal level with the location, or do that in a more open venue for others to participate. So
Yeah,
happy
and
to
that
do
might
that.
be something we consider looking into doing with where we video it as well, so that we can post that on our website, and anyone who needs
Definitely.
to go and review it could do that. So that's definitely something we would look into doing. Unless anyone in the next few seconds asks another question, I think that's it. Chris, again, thank you so much for joining us today and presenting. Always super knowledgeable and helpful. So we appreciate it.
Thank you.
And remember to download the Excel spreadsheet before we close out of the webinar. You will be receiving an email soon with the recording of the webinar and a copy of the slide deck for the presentation. So thank you all for joining us again. Our next webinar will be February 22nd. It will be presented by Joe Anderson from Reliability X, and he's going to be talking about coaching and mentoring in the reliability journey, which will be an excellent webinar as well. And he will join us on February 22nd. And that registration page is live on Seal Connect on the SEPCO website. So again, thanks for joining us. Hope you have a great rest of your Tuesday, and we look forward to seeing you next month with our next webinar. Bye, everybody.